So this presentation is obviously about image de-identification, and what that means is really lowering the risk of identification or re-identification of patients, preserving their privacy, but at the same time providing value through shared data or secondary use of data for development of analytics, and including AI ML tools. So lots of high tech in healthcare, producing a lot of data, and the challenge is how to harmonize that those data sets and share them for secondary use. And now with the NIH data sharing mandate that went into effect January of last year, this issue has become front and center for not just medical images, but a lot of medical records and medical data that are generated through NIH support that need to be shared. So again, the topic is about preserving patient privacy and mitigating risks. So de-identification is really about lowering risk, because nothing is absolutely totally de-identified unless it's, in the context of an image, if it's a white noise, it's basically speckles of white and black, but otherwise there are ways to identify perhaps individuals. So there's a legal aspect to image de-identification, and that's conforming to HIPAA, Health Insurance Portability and I forget the second P, Act, and that went into effect in 1996, and then the need at the time when we started in 2020 was to provide services for the Imaging Data Commons. That's the center box that's in yellow. It's hard to read, but that's NCI Imaging Data Commons. And then the greater need that, or the greater cause that we found since last year is to help with the NIH data sharing mandate and provide, hopefully provide investigators with guidelines and tools that they can use to de-identify their images that were generated through NIH support and share them, because most of the time their expertise is not in this area. They're experts in their own area of biomedical science, and through that they generate medical images, but at some point they need to share with the community. So early on I realized that there were more to this than just image de-identification itself as a pipeline, which was the incentive of this project, but we needed some data to test the de-identification tools that did not have protected health information or patient identifiers, because those cannot be easily shared without certain data transfer agreements and data use agreements. So the core project is the MIDI pipeline, which is the core of this presentation today that you will hear from my colleagues from Deloitte. But in the course of that project, we've also had branches into creating data sets with synthetic PHI for testing, and task group. We brought in about a dozen experts from academia and some from professional scientific societies in the area of medical imaging to make recommendations for image de-identification and best practices in the context of sharing data at the national level and through repositories such as the NCI Imaging Data Commons and otherwise. So the task group completed its work March of last year, and their 100-page report is in archive, freely available, and we're working on publishing a summary of recommendations and best practices in a peer-reviewed journal in the coming months, most likely in the Journal of Digital Imaging. And so the data sets, we started creating data sets, multimodality imaging data sets from real images from patients, but with synthetic or fake patient names and addresses injected into the DICOM header to allow testing of this pipeline. So that's the MIDI data sets. And then there's a challenge that's coming up in October of this year. It's essentially inviting tool developers for image de-identification to test their tools against this synthetic data set that we have based on certain conditions and terms that we specify to see how their tools will fare against others. It's really much of the effort has been to raise awareness about this issue and coming to some sort of standards or harmonization in terms of approaches. And then we had a virtual workshop last May, which we had 600 attendees, or 600 registered and 400 some attendees over 2 days. All the material is openly accessible, and also a report of that is in the works for publication in a peer-reviewed journal. So pretty much everything that we produce through this project are accessible. Just by way of background, I wanted to, in case folks are not familiar with medical images, just a little bit about their format. So DICOM, digital imaging communication in medicine, has been around for 38 years. It's a standard that all manufacturers of medical imaging systems, CT, MRI, X-rays, mammography systems, they follow, and that provides a specification about what is the content of the metadata in each image file, and also specifications about interoperability with medical systems and other EHR systems, etc. But at the level that we're talking about, we're looking at single files of images and then series of those and such. So in the left-hand side, there is the simplified DICOM data model, which at the very top is the patient, and then a patient might have different studies, and each study might have a number of series. Each series is a collection of images that were required the same way. So they could be sagittal scans, as shown there, the profile of a head, cuts along that axis or that plane, or it could be different parameters. But essentially, they're bunched up into a series. So each series contains maybe tens or hundreds of images, which they're also referred to as instances. And what's shown on the right is one of those. So it's an image of a subject's head. There's an MRI image, and on top, just for the purpose of visualization, showing a portion of the header, DICOM header. So DICOM header is essentially a matrix of tags that each has a content, like patient name, patient ID number, the study date, modality that was used, what kind of filter was used for reconstruction of image, etc. So there are hundreds, maybe 600-700 of these tags in each file, and not all of them have PHI or patient identifiers, but a number of them have patient identifiers, and some have pseudo-identifiers. Pseudo-identifiers are those that can only be problematic if they're linked to other identifiers and reveal a patient's identity. So in the course of the identification, you need to take actions about how to change things, like patient name obviously has to be changed, and record number is changed. Dates are shifted, because if you have serial acquisition of studies in a clinical trial, for instance, you want to preserve the temporal relationship of those studies to be able to analyze the data the correct way. So there needs to be agreement about how dates are shifted, and those are established in the guidelines. So at the beginning of this project was to set up something, a pipeline that will test the identification, and we started with data sets with synthetic PHI that's shown in the left, and then this is a simple model of image submission and de-identification, and then evaluation of the performance by third party, just to avoid bias in the course of the project. So we partnered with colleagues at Deloitte, with Dr. Jürgen Klenk and Ben Kopchik and their colleagues, and we've been through this journey for the last few years, and it's been exciting to see our progress and raising awareness about this project. So I'm going to hand it over to Jürgen to take it from here. Thank you.
Thank you, Keyvan. So just to tap into the challenge a little bit more, and then we're going to open those boxes that Keyvan showed you, what's in those boxes, and talk a little bit more about those. So this is an example of an image that it's a chest X-ray that we're having to de-identify. And as you can see, there is not just potentially PHI, PI, in the DICOM fields that accompanies that picture here, but there is some information on the image itself, right? So a reliable tool will have to identify such information and then blank it out so that you can really have both the image as well as the DICOM fields properly de-identified. Now, our medical community is very innovative, and they come up with good they ideas that make our lives difficult as trying to apply machine learning to do this task. So for example, they go and write some PHI, PII type of information into some obscure fields in the DICOM records, and there are lots and lots of DICOM fields where they put in a study ID or something like that. They misuse in some ways, or at least that's how we perceive it as data scientists, the purpose of the fields, and they put the information in there. And so your tool has to still find that information even though it's in the wrong field, and then scrub it from there as well. So the challenge that we had really in configuring, and Ben will talk about this in more detail, was to really go in and figure out what are all the various places in which PHI-PI could be found. And those best practices that Kevin already alluded to, which is that long list of how you need to handle the DICOM fields, that is basically what we had to replicate in the machine, doing that automatically and reliably. So the problem that we're facing and why, as part of the motivation is, again, imaging is becoming an ever more important modality for biomedical research. And as a result, the data set volumes are growing exponentially. While maybe in the past you could scrub these records manually, it's just no longer possible at scale, and especially at the scale at which we need those records for machine learning purposes if we want to train on those data sets. Those are going to get very large, and we need automation for de-identification. So I mentioned the privacy rules that we need to employ to remove all the PHI-PI that's in there. And then we looked at cloud-based de-identification tools. And just about when we started the project a few years back, the Google Healthcare API came around, which looked like a tool that was very useful because it could read in natively DICOM images and then scrub them with one command, so it seemed at the time. And while that probably did a good amount of the job already, the work was then in understanding those best practices in all the ways the medical practitioners found innovative ideas how to make our lives harder to find the PHI that they had buried somewhere in those fields, to find it and peel it out and scrub it in the right way. But the other point that I want to make here real quick is sharing of these images requires scrubbing the PHI-PI out of them so that they can be used for research purposes. And it's really important because there is high hope that clinically relevant results and tools can be developed from large image data collections. So here's an overview of the pipeline that we built. And so at the top you see the image data itself that sort of is fed in. It has PHI-PI in it. And then comes a tool that we use the Google Cloud Healthcare API for to do all the scrubbing. And it sort of does it on both ends. On one side, on the DICOM fields, which are text fields that accompany the image, the metadata, and on the other hand, on the image itself. And then you have sort of the validation step that needs to happen to check how well you did based on what image you processed and what the system did and what was it expected to do based on best practices. So we had a training and test data sets for that purpose and an independent validation organization. And then that produced a report that ultimately allowed us to assess the validity of the de-identification process. A couple things to mention. In that myriad of DICOM fields, you will find what's called research critical tags. Those are pieces of information that are important for the scientists if they want to use the images for research purposes. It could be information about the device that was used for imaging purposes. It could be about the patient, about the findings, and so forth on the image. What we wanted to also do is we wanted to make sure that we work with a test data set, and I think Kevin mentioned that already, that was kind of safe for us to operate with, which we used a synthetic data set for that was generated for us. That allowed us to really do the work without exposing potential PHI-PI. It led to some funny findings in the end as well. Maybe Ben will have a chance to comment on those, on some of the funny findings that happened. Where we first scratched our heads why the system was doing certain things and when it shouldn't have done it. But anyway, we'll get to that in a moment. But what we're doing now as a next step here is for Ben to come up and he'll open this box that shows the Google Cloud architecture for us. I'll actually advance the slide to that. And he'll tell you what's in there and how it works, and then we're going to walk you through some of the results of the work that we've done so far. So Ben.
Thank you, Jürgen and Kayvon. Yeah, so when we got this project, the key point of it was to build it all out with GCP native tools. This was a big point from NCI security team. They didn't want us having to import a bunch of tools outside that weren't tested and weren't based off of their security protocols and weren't approved by them. So we have used all GCP native tools here to build up this pipeline. It might be a little bit hard to see, but we import the images. Once again, we're using synthetic images, so we're not doing anything like a CTP protocol. But we're able to get those into cloud storage. And then using automation tools such as Cloud Functions, we're able to push it through, or in Cloud PubSub, we're able to push it through to the healthcare API, where the data then gets to go sit into a DICOM store. From that DICOM store, we're able to then de-identify the data and push it to a de-identified DICOM store, where then we can do our full analysis on it using Vertex AI and AI notebooks. One additional point to add here is that all the security protocols and all the logging of all the actions that were being taken, we were able to log those to identify what was happening within the pipeline. And the step that you don't really see here is within the de-identification API, there's a lot of configuration tools. So we had the de-identify API has basically 3 methods to de-identification. You can just de-identify the whole image by just scrubbing out all of the data, which is like their safest option. So basically taking the DICOM header, removing all of the data that's not needed to view the image itself, and then give that back to you. The second is their own algorithm, which is designed to de-identify the data to the best of its ability. And the third is what we did, which was actually do our own configuration of all the tools, identify the DICOM tags that we specifically wanted to scrub, as well as take certain actions on to do the de-identification. And so with that, after going through our architecture, we can dive into some of the results that we have found over the past couple of years. So the first is that the test data set that I specifically am going to be talking about is the data set that can be found on TCIA. It is open source. It is now available to everyone after we finish the first couple phases of this project. And it contains 1,836 images. And within that, we were able to find 1 false negative, which is, or 1 false negative and 9 false positives in the DICOM header, no false negatives and 2 false positives in the Burton image data. And so here, what I am showing you is the image that Jürgen introduced to us earlier, which is the chest X-ray, where we have a true positive image de-identification. And the important thing here is that context matters, where the Google de-identification tool was able to identify in the pixel data, in the burnt-in pixel data, that on the top left, there was pixel data that was considered PHI-PII. So that is the name, that is the date, and the date of birth. And it was able to remove those pixels completely. At the same time, we were able to look into the code and identify that it did recognize the text in the top right, but it recognized it as potentially critical information for the researcher and not PHI. So it was able to keep that. And so this is the power of this technology that we've been using for the API, that we're able to actually get context not only within the header data, but within the pixel data as well. We also got some funny issues with some of the images, some of them being a false positive image. So here we're not 100% sure why it de-identified. You can see the black square right in the middle of the de-identified image on the right versus what the original image is on the left. So this is an example of some incorrectly identified PHI where it's actually partially covering up the image. But this is also something that we can easily identify and have what we would consider a human in the loop to be part of this process, where if the pixel data is covering up data in an area that most likely would not contain PHI, we can actually have a human go in there, check it, and register this now as a incorrectly being identified as PHI and be able to have the image restored to its original format. So now onto the header data, and this is where we're going to get to some of the funny business that Jürgen was discussing. The first thing is to identify the green lines are all things that we were positively able to take out of the header data within its context. We can see what the tag names are there on the left. So for instance, for the first one, we have the additional patient history, able to identify the name that was in there before the de-identification, then after it. You can notice that we completely scrubbed it. At the same time, there was some also partial de-identification that could also necessarily be considered as full de-identification. So for instance, Harris Community Clinic, it did remove the name Harris, just leaving community clinic. Without context, you probably would not be able to identify what that community clinic is. So while we would have liked it to remove all of Harris Community Clinic, removing Harris was at least a partial de-identification, leaving us with just a name that might not be able to be useful for bad actors. The other interesting case, if you look at the very bottom, we got some instances where the term MR constantly popped up for magnetic resonance, and we identified that the algorithm was actually identifying this as Mr., and then everything that was following after it would actually be scrubbed. So in this case, the algorithm thought this was Mr. UE, where it actually, or Mr. breast, so it removed the word breast. One other thing is that some of our errors were also due to the nature of the data set being fully synthetic. So one of the things that we found was that the synthetic data set contained addresses or phone numbers that just were already impossible. So for instance, in this case, that number at the very top is a area code that does not exist in the United States or even anywhere. So this number is completely impossible. So what the Google de-identification tool would do is identify it as already being de-identified. And we saw this multiple times, not only just with phone numbers, but also with a lot of addresses. So a lot of addresses that were part of the synthetic data that were completely made up, the Google tool actually identified them as already being de-identified, even though we were trying to get it to de-identify something that didn't exist. And that brings us to our final results. The first thing to point out was that within this test data set, we did achieve an accuracy based on actions taken of over 99%. So actions taken are, if you see those, the chart on the right, you see tag retained, text retained. So it's if we properly retained that tag, did we properly retain text? Did we properly remove text, and did we change the UIDs, and did we shift the date to all properly? And for all those actions that were taken within the data set that we had, it was over 99%. The other big aspect of this is how long it actually took to do the de-identification. So we had a second data set that was created that had a lot more patients and a lot more images. So for the 93 patients and over 14,000 images, it took just on average 4 minutes and 6 seconds of runtime, which averages out to about 0.017 seconds per image to de-identify, which is very fast and much faster than any human would be able to actually do the de-identification. A couple of things just to note on this graph is that we tested it across multiple regions. So one aspect was using what's called a multi-region within GCP, and the other one was within a single region. So based off of latency, the multi-region de-identification would take longer on average, where whenever everything was sitting in a single region doing the de-identification, it actually performed much faster. And so with that, we have our next phase, which will be discussed back to Kayvon.
Thank you, Ben. So far we've been operating on data with synthetic PHI and focused on what's the green box here, the MIDI Google API, or data loss prevention DLP platform. And in the next phase that we are about to start in the coming weeks, we'll be using real data with real PHI. And so it's taken about a year to have the data transfer agreements in place and other logistics checked off to be able to do this project, including security assurance by the security teams that everything is compliant, both on the Google Cloud side as well as NCI, NIH. So what we are trying to do is to benchmark the performance of, first evaluate the performance of the MIDI pipeline on data with real PHI, real original data that's not been processed, and then compare its performance to TCIA. TCIA, that's been mentioned a couple of times, is the Cancer Imaging Archive, which has been around for 11 years, and it's very well known in the community of researchers for access to imaging data. So that's the other imaging repository that NCI has, and what we are focused on is Imaging Data Commons, which is cloud-based. So if you imagine a diagonal line across this graphics, the upper part, the purple boxes, and the CTP box that's brown, it's the way TCIA operates. So once the data submitter agrees to, once data submitter is approved to submit their data to TCIA, TCIA provides a local version of CTP, which is an open source de-identification tool developed by Radiological Society of North America many years ago, and it's sort of standard in the community. So you can set the profile for CTP to de-identify to the level that you want, and it's compliant with our legal requirements, etc. So TCI makes a version of the CTP available locally. The institution de-identifies their data set images and sends it to TCIA, and they do a second check or the screening of the de-identification, and then they publish the data after some quality assurance measures, like checking for any burn pixels, etc., that might be in the data set or what have you. So, and then in the lower part of the diagram is the MIDI operation. So what we want to do is to compare the performance of MIDI to TCIA and adjust that profile. That's the delta that's shown on the right, to adjust the de-identification profile until the output of both arms of the experiment are identical or the differences are acceptable. So that way we can benchmark against TCI, which by far is really the community standard or gold standard for image de-identification. They do a great job of curating data. So this is the next phase. It's going to include 300 some subjects with multimodality images. And once we do that and show that feasibility and efficacy of de-identifying real data sets, then the next steps would be to take measures for putting this into production and operationalizing it. But so there are several steps after that could be explored, and those include developing an end-to-end data curation, data submission, de-identification, and quality assurance pipeline that could take care of not only DICOM images, but also other medical images, including digital pathology, which was mentioned this morning. And those, in some ways, are easier to de-identify because they have a label slide, and typically that could be blurred out or de-identified in other measures. And very rarely, especially nowadays, there's markups in the slides that pathologists might have made, and those could be done, dealt with optical character recognition that Ben talked about. So there's a lot of possibilities once we get past the next stage. And although we started with the incentive for this project being providing image de-identification services to the Imaging Data Commons at NCI, but because of the data sharing mandate, we now have a bigger cause and really want to be able to provide some service to the community of scientists, NIH scientists, to be able to share their data. And we find that this to be in resonance with the ARPA-H that was mentioned, their biomedical data fabric, which is about best practices in standardizing data curation and provenance, etc. So there's more roles for this kind of approach. And I think that's the last slide. I want to acknowledge there are many people involved with the MIDI project and several teams. Obviously, folks from NCI, Deloitte, Ben Jorgen and colleagues at Deloitte that are listed. want to acknowledge the help of folks at Google, including Dave Blardo and Patrice and Cheryl Corman. And of course, we have people like Dave Clooney, who's the editor of the ICOM standard and very interested in image de-identification, involved with this project, and Fred Pryor, who's the principal investigator of TCIA, because they're looking at ways to also hopefully modernize their approach to image de-identification. And the reason we chose Google Cloud initially was because the Imaging Data Commons is implemented on GCP, so it was a natural choice. But through the course of this project, we've learned that although other cloud providers have some de-identification tools, but really the Google Healthcare API is perhaps the most advanced and also most customizable. And even with that, we're working on improving the process. So that was the reason we went with this choice. But really, the cloud approach is to make the identification scalable, because the TCI operation, for instance, is a combination of man and machine in the identification. But to me, that this is a routine, repeatable process that's all digital. So there's really, we should be able to automate this process as much as possible and really take advantage of AI enablement of the process, because the more that the system trains on additional data, the more robust it will become. And then you can address other things beyond the identification. So I'll stop here and thank my colleagues and you for your attention. Thank you.
You're crossing institutes in NIH. This means that you probably want to operate these pipelines in the same Google region, regardless of the institute. Is that how you see it evolving?
In the same cloud region, you mean?
Yes.
I think that has mostly to do with the economy of scale and how much it will cost. But yeah, those have to be decided. So the example that Ben showed was operating in the, I think, West Virginia, or on the East Coast region, central region of GCP. But yeah.
The other question is, I was puzzled by the 17 milliseconds per 200 all slide image. I'm guessing this has something to do with the parallelization, right? The model cannot be that fast, or is it?
Hello. Yeah, so first, the model is very fast, but yeah, it is also parallelized. So it's a serverless function, so it gets to scale with how many images we have in the available compute that Google is basically allowing us to use.
Okay. You don't know from the logs how many machines were involved?
We could check. I didn't take a look, okay. But we can look.
Thank you.
And maybe, Jonas, for the, if you noticed on the multi-regional, that was almost a tenfold, factor 10 slower. If we happened to get into the region through a multi-region setup in which the healthcare API was actually natively deployed, then even the multi-region was pretty fast. But if it happened to be picking a region where that wasn't the case, it needed to sort of work around, and that caused some of the delays.
So as you go through your project, you're really making a nice set of data that includes images with PII and their de-identified counterparts. Have you tried re-identifying the de-identified images so that you have confidence that they're truly de-identified?
We haven't got to that point yet, because so far we've been dealing with synthetic PHI, but after the next phase we could do that. There are people who are interested in re-identification as a way for quality assurance of the identification, I suppose. I think that's a worthy effort. Be, going down a rabbit hole, because there could be so many different approaches to de-identification, re-identification. So it depends on use cases, I guess. But that's an important point. Yeah.
The best practices that were developed together with Dave Clooney and others really are focused on making sure that that is as hard as possible. As you probably know, head CTs are already clear that you can easily reconstruct an image out of that, and you almost see the actual person then. So no matter what you do there, you could probably re-identify that, and see the individual in front of you. So those are things where I guess organizations such as the Imaging Data Commons will have to decide how to handle those types of images then in the future.
Yeah, but even tools like defacing could be incorporated into this pipeline. So if you have a head and neck scan, then it would trigger the defacing protocol or algorithm and would deface the. Defacing is essentially blurring out the facial features of the subject in every slice, so you cannot reconstruct the face through 3D reconstruction and match it with the photograph of the person.
Hello, Chun Ding from Celerons. So do patients need to consent for their data to be used?
Yes, these are consented before they're shared, of course. But once they're shared or de-identified, then the data is no longer human subject research. It's not considered human subject research once it's de-identified.
Are there any regulations or requirements you need to consider, such as GDPR or similar?
I'm not familiar with GTP.
GDPR is European.
Oh, GDPR,
data,
yes.
Yeah, privacy.
We are focused on U.S. use case right now, and GDPR, from what I understand, doesn't specify specific actions to be taken. It provides some guidelines, but it's much more restrictive than HIPAA, what we understand. So in our workshop, we had representatives from EU and Canada to talk about their approaches to image de-identification.
Thank you for sharing all that. Appreciate it very much. This is Hemant Bundele from IB Launch. You might have shared this, I might have missed this, but I'm going to still ask, what tool are you using to identify the text on the images and then remove?
I believe it's an OCR tool, optical character recognition.
Any specific or?
I don't know the specifics. I don't know if Ben does.
It's all contained within the healthcare API.
Yeah, so the Google Healthcare API sits on top of Google's data loss prevention service, and it's an embedded function that we call, that is pre-trained by Google on doing precisely what we showed you for the imaging data, just for the pixel data. For the DICOM headers, that's where we went the configurable route. So we heavily configured it to make sure that every DICOM field would be de-identified as per the best practices. But the imaging part is a pre-trained algorithm by Google and provided as the healthcare API as a service.
So the use of DICOM is critical, right? That image.
Correct.
Okay,
Yes.
got it. Thank you.
Although the healthcare API can take other modalities, you can take FHIR as well if you have textual data.
Yeah, and that's another
records.
point of, interest, because we want to think beyond imaging. And if you are collecting medical records, then you can de-identify EHR data, presumably. Well, thank you.
Thank you.